A quantum discovery unifies two opposing realities.
Physicists at the University of Heidelberg, Germany, have just presented a groundbreaking theory that finally connects two seemingly contradictory views on the behavior of exotic particles in complex quantum systems.
This unification solves a puzzle that has puzzled scientists for decades and opens new doors to understanding matter under extreme conditions. In the quantum world, when we place a single different particle called an impurity amidst a sea of many other identical particles, called fermions, like electrons or atoms in certain experiments, two opposing scenarios emerged in previous theories. In one case, the impurity moves freely through the system, it interacts with the particles around it, which organize themselves around it in a coordinated way. This creates a collective entity known as a quasi-particle-specifically, a Fermi polaron. It's as if the impurity drags along a cloud of neighbors, forming a package that moves together, maintaining a certain order and mobility. At the other extreme, when the impurity is very heavy and practically stationary, something dramatic happens. It profoundly disturbs the wave functions of nearby particles. This effect, known as Anderson's orthogonality catastrophe, disorganizes the system to such an extent that quasi-particles cease to exist. The impurity behaves as a fixed and immutable perturbation, destroying any possibility of organized collective movement. For a long time, these two scenarios were treated as distinct realities, without a clear link between them. Scientists could not explain how the transition from one to the other occurred, nor when exactly a quasi-particle emerged in extreme situations.
Now, a team led by Professor Richard Schmidt of the Institute for Theoretical Physics at the University of Heidelberg, with the participation of Eugen Dizer and other collaborators, has developed a unified theoretical model that resolves this conflict. Using advanced analytical techniques, they demonstrated that, in practice, no heavy impurity is completely immobile. There is always a subtle, even minimal, movement caused by the adaptation of the quantum environment around it. This small displacement generates an energy gap, a kind of barrier or energy difference that prevents total catastrophe and allows quasi-particles to emerge even under conditions previously considered prohibitive. Thus, what seemed impossible becomes possible, order emerges from chaos, and the two opposing realities connect in a single theoretical structure. The work applies to different spatial dimensions and types of interactions, from ultra-cold atomic gases, used in laboratories to simulate quantum matter, to modern two-dimensional materials and advanced semiconductors. This deeper understanding can aid in the interpretation and planning of real-world experiments, accelerating the development of quantum technologies, such as new materials with exotic properties or devices based on collective quantum effects. Published in the journal Physical Review Letters in November 2025, this breakthrough demonstrates how, even in extremely complex quantum systems with strong interactions, small nuances can restore order and reveal surprising behaviors. It is another step towards deciphering the secrets of matter at microscopic scales, where the rules of classical physics give way to collective and emergent manifestations.